Hello, everyone, and welcome to Abbott's live webinar of Troubleshooting Industrial Furnaces. We're going to go ahead and get started here. I do want to let you guys know that throughout the presentation, if you have any questions that you would like answered or would like addressed with our presenters today, up in the left hand, I believe, drop down, you guys, there should be a Q&A section. If you click in there, you can type your question. We'll be able to see it and then hopefully try and address it during the webinar. If for some reason we're not able to, or we run out of time, we will follow up afterwards, send you an email, get in touch with you in regards to answering that question. So I'll go ahead next here and introduce our presenters that we have. Buzzy Lewandowski, Technical Sales Engineer, Brian Smith, Applications Engineer, Dean McLean, our Electrical Foreman, Andy Benson, Electrical Supervisor, and Matt Pavlock, our Field Service Manager. So we're going to go ahead and just jump right in, and Brian's going to go ahead and get started.
Good morning, everybody. Today we're just going to kind of go through an overview of the furnace and look at the different components and their functions. As you can see, there's just a schematic there of the load end, the preheat section of the furnace, where we're going to remove the binders and preheat the product. And then the high heat, where we're going to reduce the oxides and bond the particles or melt the braze. And then the cooling section, where we control the cooling to avoid oxidation, set the properties, and then the product exits out. I'll turn it over to Dean, and he'll talk a little bit about temperature profiles.
Morning, everyone. So, temperature profile, or what they call them nowadays, is a TUS, which is a temperature university or universal survey. It's just done with, we run thermocouples down through the center of the furnace, and it'll graph out on whatever kind of data recorder that you're using, the temperatures as it goes down through there. So this one here is showing just a simple 3-zone box. Yeah, 3-zone single box, sorry. You can see as the temperature, as your thermocouples go in at your hood, temperature just kind of gradually increases to whatever your temperature was in your high heat box. Comes back down and out of the cooling. That's just a basic one box, what you would see profile for that. So this is a two box, 5 zones, so it has a preheat and a high heat. And the marks that you see on there, what we do is we actually go down through and measure out the different events. We start at the front, which would be your 0 mark. That's when it first enters the hood. And you measure down to, whatever it is, your preheat, and your thermocouples down through, you exit your preheat box, enter your high heat box. So those measurements are all just taped onto our thermocouple. And then as it's going through, we hit an event button that gives us that mark on there, so we know where the tip of the thermocouple is as it's going through the furnace. As you can see on this one, you go, into your preheat, kind of ramps up to about 800, and then it in between your transition zone, you always get the little dip there, just because you're coming out of the one box and before you get into the other. Then it just goes up, kind of stabilizes, for whatever you're you're looking for your time and temperature. Comes out of the high heat box and through your coolers. What we typically do, I think, go to the next one, isn't there? Yeah. So what we typically do is, on a new furnace, when we set it up, we'll run a profile. It's just basically to get a baseline so that we see what the furnace is doing, when it's brand new. That way, in the future, we typically run them once a year, a profile. And then you compare the two profiles and you can see if, you're getting something cattywampus with your temperatures, or, you can, one side's cooler than the other. And there's different things to look for, spray bars get plugged up, insulation drops. This will, help you determine what's going on inside there with that temperature profile. So the equipment that you need, I guess, is some kind of a data recording device. We use a couple different ones here. One we have we can do up to 9 thermocouples on it. The other ones we can do up to 6. Typically, we run 3 on a conventional furnace. The other thing you need is the thermocouples that are the proper length. And again, with those, we roll them out next to the furnace and we put all those marks on there so that, as you're going through there, you can mark all those events and you can see where your temperatures are at your different spots throughout the profile. And then we use a fixture, and that's supposed to replicate like the temperature that it's seeing on the inside of the part. It just kind of keeps it out of, the direct heat, and it's got to transfer its way through. So kind of get more of a realistic idea of what your part's actually seeing as it's going through there. So we typically, when we do it year after year, we like to have the settings around the same thing with your belt speed, your temperature set points, your atmosphere flow, whether you run it empty or with a lot of people running with scrap or dummy parts. We like to do it the same way year after year. That way you can, basically lay the two profiles on top of each other and you can see, if there's anything going on and what part of the furnace that you may be, you may be having an issue or something is, starting to look like it's going to be causing a problem, I guess. So, after you have all your conditions and everything set, then you mark off take the measurements off the furnace, you put it onto the thermocouple. And then we just use a thermocouple wire and we strap it down onto the belt. We usually do 3 of them. We'll put 1 in the center and then 2 on, 1 on each edge, probably anywhere from 2 to 3 inches in, just to, that way you get a temperature across your belt. And then you just, once you got everything strapped on and tied down, you start the belt up again, start the profile recorder, and as it's going through, you just keep an eye on it. And when your tape marks get to the hood, you hit a button and it gives you that vertical line so that you know where you're at as the profile's going. So yeah, we do them on a new furnace, right at startup, so that we get a good baseline. Then we recommend that you do it at least once a year, just so you can, kind of like a preventative maintenance, you can keep an eye on what's going on inside the furnace. So it helps you before you end up with a major problem that you're running into parts coming out bad or whatever.
So here we'll talk a little about the atmosphere and how it relates to the zones of the furnace and the temperature. So where we saw, the graph as we enter the furnace into the preheat, our temperature is gradually increasing, and if we're talking about centering, this is where we're going to remove those lubricants and flush those vapors out of the furnace. So the red line on the graph there signifies the temperature. And as we're in the preheat box and the temperature is increasing, you can see the black line is measuring the dew point, the measurement of water in the atmosphere. So as those lubricant vapors are coming out of the product into the atmosphere of the furnace, we want to have a high dew point there so that water vapor reacts with the carbon vapors coming out of the product, and it helps to maintain that in a gas form to flush those lubricant vapors out of the furnace. The blue line there signifies the amount of hydrogen in the atmosphere. So we want to have hydrogen available in that front end, again, to react and help flush those lubricant vapors out of the preheat zone. You can see the red line as it makes the dip there from the preheat box into the high heat box, where there's no heating elements between the two boxes. Our temperature drops off a little bit, and then as we enter the high heat, it's starting to increase. So now, as our temperature is increasing in the high heat to get us up to temperature to bond those particles, we have to have a very low dew point because we don't want to get any oxidation on those particles. We want to keep everything nice and clean so we get good bonding. So here's where the hydrogen is important, because we have to clean those particles, remove that oxide layer off of the particles so they can bond and not have that oxidation layer preventing the bonding. So this is where the hydrogen is important in the atmosphere. As we go through the high heat box, we hit our peak temperature, our centering temperature, our brazing temperature, and then we go into the cooling zones. Now our temperature starts to drop. As our temperature is dropping, our hydrogen's dropping, because we need the hydrogen up toward the front of the furnace to help with the lubricant removal and help with the reducing of the oxides in the particles. So in the cooling zones, we don't need the hydrogen. So we'll talk more in the slides coming ahead about atmosphere balance and how we set our rotary injectors to keep that hydrogen up in the front of the furnace where we get our biggest bang for the buck for it, where it's needed. And then as we're in the cooling zones, you can see the dew point, again, very low, very dry atmosphere, again, to prevent our product from getting any oxidation buildup. If we have a higher dew point back there, that's where we see discoloration and decarburization. So we need a very dry atmosphere in the heat box and then into the cooling zones. So that graph just kind of ties, again, the temperature in relation to the dew point in the atmosphere, and then the hydrogen content of the atmosphere. The atmosphere functions in the furnace, why we have to have atmosphere in there. Normally a nitrogen, hydrogen mix of some sort, whether it's gases or generated atmosphere of DA or endo. We have to have atmosphere in there, again, to prevent oxidation. As that temperature of those metals increase, they become more susceptible to oxidation. So we have to have the atmosphere present to prevent any oxidation on those metals. Excuse me. In the powder metal industry, with the lubricants used in pressing the product, we have to remove those lubricants to be able to get clean particles so that we can get bonding. So that hydrogen in the atmosphere is reacting with those lubricants coming out of the product to prevent buildup in the furnace, to prevent oxidation on the product. So it helps with the delubrification, and it keeps the furnace clean, because we want to keep that lubricant, we want to keep those vapors in gas form so that we can flush them out of the furnace and up the stack, as opposed to them dissociating, getting carbon, getting soot, getting built up in the front of the furnace. So the atmosphere plays a huge part in keeping the furnace clean as well. As we increase the temperature up to our bonding, our centering temperature, those particles are all going to have a coating of oxide on them, usually from the water atomization of the powder. So that hydrogen in the atmosphere, the reducing gas, it's going to reduce those oxides off the particles in the parts, so that we can get the bonding when we get up to temperature. And we're also using it for carbon control, right? So if we have a high dew point in the furnace or air in the furnace somewhere, then we start running into issues with decarbonization, right? The oxygen is going to attack the carbon in the product, and it's going to remove the carbon from the metal, and it's going to make the parts soft. It's going to make them rejects. So those four are the primary functions of why the atmosphere is in the furnace. This is just a picture of one of our atmosphere carts. A lot of people in the industry in the area, they'll when they call us and they have issues, we bring one of these in, and we can use this to diagnose the issues in the furnace if it's atmosphere related. Some of the capabilities of this are, so we come in where there's 3 meters on that cart where we measure the oxygen level in the atmosphere, we measure the dew point, the water content of the atmosphere, and we measure the percent of hydrogen in the atmosphere. We can also use it to hook up, it'll record, it works as a recorder if we're doing temperature profiling. They're primarily for atmosphere, diagnosing atmosphere problems. So when we'll see some more graphs here coming up about atmosphere balancing. We talk about having the hydrogen up in the front of the furnace, in the heated area of the furnace, to help with those oxide reductions and delubrication and removing those lubricants from the furnace. We'll hook these up, and this is where we'll look at the atmosphere balance to make sure that we have the correct amount of hydrogen in the front of the furnace, that we don't have air leaks coming in from the front door or the back door of the furnace. We use those to adjust the rotaries to optimize the atmosphere and balance the furnace. Again, we're measuring the composition. We look at the hydrogen content in the furnace to make sure that there's no air leaks that are consuming the reducing gases or the hydrogen, or water leaks that are causing issues with the composition of the atmosphere. And again, we use this to optimize the gases in the correct part of the furnaces where they should be, because the atmosphere and the gases are very expensive. So we want to make sure we're optimizing that and getting you the best amount of work on your product for the cost of the atmosphere. Again, with the same as the temperature profile, when we go out, we set up a new furnace, we'll do a baseline at all the furnaces in production, if you can do this and have a baseline data, so we know what the atmosphere composition is in each part of the furnace. When you're getting good product, then when you have to do a troubleshoot or you have an issue, you have that baseline to compare to, and it helps you diagnose quicker and reduce your downtime of what you need to change, replace, fix to get back to the baseline where you're making good product. So again, we start out, we check the dew point and the oxygen level of the incoming gases on the lines, make sure there's no leaks anywhere from the generator or the tank through the plumbing, to make sure that the gases are clean and pure when they're going into the furnace. And then we use that to help determine the temperature profile, the atmosphere flow. Excuse me. The atmosphere flow will affect the temperature in the profile. If we have discrepancies in temperature from the left side of the belt to the right side of the belt, a lot of times it's atmosphere flow related, where an injector is plugged or not set properly, or something atmosphere wise is causing you an issue that you're seeing temperature variation across the belt, across your product. And then our furnaces, when we have them, we have multiple areas of the furnace where we have ports that we can hook up to pull samples from, the cooling sections, the preheat sections. And we'll check each part of the furnace to make sure that, again, that the hydrogen is up in the heated zones in the preheat and the high heat, and it's minimized in the rear of the furnace where it's not really doing any good to maintain the quality of the product. This graph here just shows before an atmosphere balance, the hydrogen line at the top there in red. There's the same percent of hydrogen at the front of the furnace as there is in the rear of the furnace. So that hydrogen is very expensive, and being at the back of the furnace, it's really not doing anything to help with the quality of the product. We need the hydrogen up toward the front of the furnace. The oxygen line, again, is kind of even from the front of the furnace to the rear of the furnace. It is similar across there. So we want to keep that oxygen lower at the rear of the furnace to where we're going to oxidize the product in the cooling zone. So we want that oxygen up toward the front of the furnace to where it can react with the lubricant vapors and help keep that in gaseous forms. And we don't want oxygen in the high heat of the furnace because it's going to inhibit the reduction of the oxides in the powder. And it's going to cause decarbonization. And then the bottom, the green line, you can see the dew point is a little bit higher in the front of the furnace where we like to see it, and then it tails off as it goes through the furnace in the rear. So this is what your graph would look like before a balancing, and then we'll do an after when we hook the carts up and we move the rotaries around and kind of optimize that atmosphere flow. Now you can see the hydrogen is up in the front half of the furnace. Then when we hit the curtain box in the furnace with the first curtains where we have that barrier, now you can see the hydrogen drops off to almost zero. So we're pushing that hydrogen forward where it helps with the product. To get the oxygen line, it stays pretty consistent throughout at a very low level. Now our dew point, you see where we have a little bit of higher dew point up toward the front of the furnace in that preheat box or delubing box, to help react with those carbon vapors coming out of the product. And then in the back, in the cooling section, we have a very dry, very low dew point to not oxidize the product coming through the furnace. So some of the problems that we would see in the product that would kind of point the finger as an atmosphere problem, you'd have an atmosphere problem, you'd have a temperature problem. So to look at an atmosphere related issue would be the product, right? If the parts aren't the correct color, if they're frosted or gray instead of nice and silver and bright and shiny, there's different forms of soot, depending on what zone of the furnace that the carbon is not being taken care of by the atmosphere. We'll have different forms of sooting that we'll talk about. A lot of the powder metal guys that are on the line, they're familiar with blistering. When the lubricant isn't able to work its way out of the part at a lower temperature, and when the part gets up to a higher temperature and there's still lubricant available in the part, it boils and it blisters the surface of the part, trying to escape. When it goes from a liquid and it hits a certain temperature, it becomes a gas. It almost erupts out of the interior of the part like a little volcano, and it causes blistering on the surface of the parts. We have oxidation. So this would be discolored parts, blue parts, purple parts, gray parts, yellow parts, depending on the temperature that the oxidation takes place, it'll discolor the parts to a certain color. We have belt oxidation. If you oxidize the belt, that could cause oxidation of the product and reduce your belt life. Inadequate center. If we don't get all the oxygen removed off of those particles and have clean particles to bond to each other, and we have spots in the product where we're not getting a good oxide reduction, we're not going to get good bonding. So we'd have an inadequate center. We could have, parts that are failing a physical test, like a crush test or a brake test, low hardness. They could be related to inadequate center. And then decarburization is where there's oxygen present in the atmosphere somewhere that's removing the carbon from the product and making the part soft due to the carbon removal. So we'll just kind of touch on each one of them briefly. You can see in the picture, the part on the left is kind of a dull gray color, and the part on the right is the nice silver, shiny, what we're used to seeing kind of part. So frosted part is going to have a lower hardness. It's probably not going to be, to your minimum requirement. And when we see frost, or we see that dull color, that points us toward something happening in the preheat or the lower temperature front zone of the furnace. And what happens to cause that kind of dull finish is we're oxidizing the part at the front of the furnace, and then when it gets back into the high heat, there's so much oxide that it's not able to reduce it all off of the surface. So that's why we kind of get that dull gray look as opposed to the bright shiny look. That's more than likely is caused by air at the front of the furnace somehow, either through air getting in the front door or down the front stack, or a hole in the preheat muffle, or somewhere air can get in there. We're getting too much oxygen in the front end of the furnace. Sooting, we talked about, there's some different kinds of sooting that we'll see in the next couple of slides. Soot is caused by improper or incomplete removal of the lubricant from the product. So that lubricant, as it gets hot, it breaks down into a carbon. So if that lubricant's not kept in gas form and flushed out of the furnace, if it somewhere along the line turns into a solid, it's going to turn into a carbon or a hydrocarbon. And then as that cools down, we'll see different kinds of soot. There's staining, there's black soot, which is black snow, and then the blistering is caused by the lubricant, and that's considered a form of soot as well. So the staining is, you'll see in the part here in the picture, is the stains on the part. You can't wipe that off. It's kind of stuck on there. It's all over the part. This would take like a secondary operation to remove that, maybe like a tumbling or a vibra deburr or something to be able to clean that off. So what causes that is our dew point is too low in the preheat. Our atmosphere in the preheat is too dry. So there's no oxygen or water vapor. There's nothing there to react with that lubricant vapor as it comes out of the furnace. And what happens is it gets pulled to the surface, and without the atmosphere there to remove it, it just gets to a higher temperature and it just decomposes right into soot. It just goes into a solid form on the surface of the part. And if you look at that very closely, you'll see that they almost look like droplets. So as that lubricant comes out, it's in a liquid form, and then the atmosphere would flush that off of the surface. And if we have an atmosphere issue or nothing there to react with it, when it hits the temperature it decomposes that, it's just gonna go from a liquid to a solid right onto the surface. So, some ways around that are, is to lighten the load. Less parts is less lubricant, is maybe, gives it more atmosphere to be able to react with it. If we're running the belt too fast, it just doesn't give it enough time to work out to the surface and decompose and flush off. Or maybe it's, there's just not enough time. The preheat box is too short for, the belt speed setting that you're running. So the black soot, this is more of the black snow. This is, the kind of soot you could blow it off with an air gun, wipe it off with a rag. So what happens again is, we have the dew point in the front of the furnace is too low. There's not enough oxygen available to react with those carbon vapors. The carbon vapors work their way out, and if not enough atmosphere velocity is going forward to flush it out of the furnace, it'll kind of get carried back through the preheat and the high heat. And then when it gets into the cooling sections and it starts to cool, those vapors, they'll solidify and it just falls on top of the parts like black snow. So, one way to fight that would be to look at that atmosphere balance and get more forward flush to push that stuff out the front of the furnace and up the stack. Again, it might be slowing the belt down to allow more time for that delubing process to take place. Blistering, rippling, again, it almost looks like, if you look at it under a microscope, it almost looks like little cracks on the part. So what happens is the lubricant just doesn't have enough time to melt and become a liquid and work its way to the surface and be flushed away. It just goes from a solid to a gas, and then the gas will work its way to the surface. It'll kind of pop its way out of the part, and it'll rupture the surface of the particles as that gas escapes. Again, it's just maybe preheat settings where you're just getting too hot too fast, your belt speed's running too fast, or your load is too heavy to allow the delubing process to take part. Oxidation, again, this is caused by air somewhere in the furnace. It's going to appear as different colors depending on what temperature the part is. When it comes in contact with the oxygen, the parts are going to turn a different color. So we'll show you a chart here where if we see the gray and blacks, we're going to have this happening at higher temperatures up toward in the high heat, the end of the high heat. And then as they get lighter golds, this would be back toward the exit door of the furnace, more likely like a worn curtain, or just the belt running so fast that the parts are coming out a little bit too hot and they're just oxidizing. There's just some pictures of some different surface oxidations. Again, you're going to see the golds as the air is coming up the exit end of the furnace through maybe the curtains being worn. The lighter golds, the product is fine. They just have a darker color to them. Sometimes you'll see it on the top of the part, and you'll take it off of the belt, and the belt side will be silver, just as the air runs over the top of the parts. Again, this is when we have air or water up toward the high heat where parts are at a higher temperature, and this is where they're going to turn black or maybe even be kind of flaky and scaly. Is that parts at a higher temperature, the oxide's going to react a little different with it. Belt oxidation, Yeah, you can see the belt on the right is, it's darker, it's golden blue, so that belt's being oxidized. And the belts have they're stainless steel and they have chromium in them. So your iron parts may be nice and bright and silver, but your belt is a darker color. Excuse me. That's just going to show that there's a very, very fine oxidation occurring to where the stainless steel is more susceptible to oxygen. So the stainless is going to be oxidized. The parts are still going to be clean. As the leak gets worse, it's going to start affecting the iron as well. Decarburization is a pretty common term in the industry, in the powder metal industry. So we're talking about a loss of carbon on the surface of the part. And we're going to see a loss of hardness. Carbon makes steel hard. So when we lose carbon, we lose hardness. And again, decarburization, oxygen and carbon love to combine with each other. So if there's any oxygen available, it's the first thing it's going to attack is the carbon. And again, in different areas of the zone, if we have a high dew point in the hot zone from air getting in somewhere, if we're using a generated atmosphere, it could be the ratio is off a little bit and we're getting a little bit too much CO2, which is breaking down into C and oxygen. So it may be generator related if you're generating atmosphere as opposed to using cryogenic gas. A couple troubleshooting tools we use here. People will call in and say their parts are coming out oxidized. They're not sure. They'll think they have a water leak. They'll think they have an air leak. They're not sure. This is just one of the tools we use to help determine if we are looking at air or water. So the process is we reduce the temperature to 1900 in the hottest parts of the furnace. Copper melts at 1980, so we just have you reduce the temperature a little bit. We like you to go to a nitrogen atmosphere so that there's no reducing gas available to kind of miscue the readings. And so we go to a nitrogen atmosphere and we'll put a piece of copper, a piece of steel, and a piece of stainless steel on the belt, let them travel through the furnace. And then we'll look at the oxidation on each strip. If we have air in the furnace, the copper will oxidize. It's going to turn not shiny. It'll be kind of a frosted, dull copper, and the steel will oxidize. If we have a water leak in the furnace or a high dew point, the steel will oxidize, but the copper will stay clean. And then if there's just a very small leak, more sensitive leak, the stainless is going to discolor. So that kind of helps point us in the direction of, now are we looking for a water leak or an air leak? Some things we do to help with inadequate center. Maybe, there's something going on in the furnace, some insulation moved like Dean talked about, and we have a centering temperature that's too low. It could be a faulty reading on instrument that we think we're at temperature and insulation moved, or maybe we have a thermocouple going bad, something that we're not seeing the temperature that we should be seeing for whatever reason. If we don't have enough hydrogen in the furnace, again, we're not going to be able to clean those particles, reduce that oxide off the surface of the particles for them to be able to bond. If we have too high of a dew point from either an air leak or a water leak, again, we're going to oxidize those particles and not allow them to bond. If we're not getting enough time at temperature from the belt running too fast, again, we're not gonna be able to bond the particles. So a test we do on this to just kind of maybe help us diagnose the problem there is we'll take a couple parts with a copper piece. We'll do one on a green or an as molded part and one on a centered part that's already been through the furnace. And we'll put the piece of copper on top of the parts, run them through the furnace, and then we can just look at what happens, right? If the copper does not melt, we have a temperature issue, right? So we're not getting to 1980 to allow the copper to melt. If the copper melts and goes into the centered part, but not the as molded part or the green part, then we have a delubing issue. So if we don't get the lubricant removed from the product, there's no porosity for the copper to be able to go into, because it's still going to be taken up by lubricants. And if the copper melts and it doesn't go into either part, if it just kind of runs over and you get 2 gobs of copper and 2 silver parts that come out of the furnace, then we have an issue with the reduction power of the atmosphere, not enough hydrogen. It's either not in the atmosphere to begin with, or it's being lost to an air leak or to something happening in there. And then if we have the copper infiltrates into both parts, but both parts are oxidized, then we have a water leak, because the water will affect and oxidize the copper. So I think we kind of ran through that a little fast. Matt's going to talk a little bit about preventative maintenance to help you not have any of the issues from the previous slides.
Good morning, everyone. I'm going to just go over a couple little routine preventive maintenance that we like to see people do in their furnace to help optimize the furnace and what you can do with it. I mean, as you can see, the overall cleanliness of the furnace and the furnace area is very important. You got accumulation of dust, powder, debris can cause serious problems in the operation of the production, of course. So what you want to do is you want to clean out all the dust, the dirt and parts from the front and back ends. On that note, most furnaces have a debris tray on the front and back. I have seen where they were actually filled all the way up. They weren't cleaned out. And then debris tray were actually dragging that dust and dirt and everything into the furnace. And of course, what that does is start building up inside your furnace, which, later on leads to your belt kind of filling, maybe, or getting, built up underneath and ripping your belt in half. So of course, Abbott, we do recommend each operator visually inspects the overall condition of the furnace at the beginning of each shift to just make sure everything's supposed to be where it's at and where it's supposed to be doing. Again, using the dust on that, I do recommend using a vacuum cleaner to clean all the dust and powder of the parts of the furnace. You do not want to use an air hose. Of course, you're trying to blow the parts off up front. Some of the operators may by mistakenly put some air through the front of the furnace, and of course that'll maybe scrap that load. And very important to use a vacuum cleaner to keep the air out of the front of that furnace. Go in and check for the misalignment of the drums of the furnace belt. If you might have your belt walking back and forth, you might notice maybe some of the springs on a pinch drum might be bad. Maybe a pinch drum is not pinching the way it should. That'll kind of go right along with the next one, the drive belt. I mean, we just had one that the drive belt does have a rubber coating on it. The belt kept slipping. He didn't know why, but here that rubber actually was gone, and he had a hard time getting the belt not to slip. So that's just little things you can look at every time you walk into a shift to see if all the drums and rollers are going the way they should. Also, the drive motor and the gearbox, make sure there's no excessive heat, make sure there's no noises on the gearbox. If they do have it, I mean, it's probably time to change it on a scheduled shutdown instead of having a catastrophic failure. It's going to keep you down for a while. They got curtains in the back of that, and I'll get off Brian here a little bit as he's talking about the gold parts here a little bit ago. I'll say about 75 to 80% of the calls I get for the gold colored parts is their curtains in the back are either worn or they just got to be lowered down. One good check you can do is when you go to the back of the furnace, you can look through the rear of the curtain box And if you actually do see the red up in the high heat section or in there, you know your curtains do need adjusted. Or if there could be wear in them from your different part sizes, it's very important to keep them up to date and maintained. Of course, you want to clean and check all the hoods with all the atmosphere coming up through. Any buildup on that after time, over time, could cause you a fire in the hood or even in the stacks. And of course, you want to check the thermostats, the pumps and the gauges and other lines and leaks as repair is needed, because sometimes they will leak after running for a while. Also, you want to check the pressure of the atmosphere supply to ensure that it matches the pressure rating of the flow scope. They do, as you can see, nitrogen, hydrogen, and natural gas may be supplied at different pressures. You could have some pressure drops in your atmosphere, and of course, Brian was just saying there, I think you realize how important it is to have a good atmosphere into that furnace to keep everything running the way it should. I'll let this go here. We got some electrical maintenance here. I'll let Andy Benson take over on this one.
Hello, we'll talk a little bit about thermocouples, also troubleshooting zones. We will start off with the type K thermocouples. We recommend that they get changed quarterly. They will start to drift after a while, and a lot of that depends on how hot of a temperature that type K thermocouple is seeing. If you find they drift pretty often at the higher temperatures, we could switch to like an R thermocouple and get something to last a little bit longer in there. A lot of the calls that we get are for zones lagging in temperature. That can be caused by quite a few different things, but there's some visual checks that you can do first. One check that I would do right away is make sure your over temp controllers are satisfied. Occasionally an operator may go push some buttons on an over temp controller thinking that they're going to lower the temperature in the zone, but what they really do is just lower the threshold or limit for the over temp controller, thus tripping it out, so you don't get any power to that zone. Another visual check I would do right after that is look at my current or amp meters. We want to see the current on all three legs pretty uniform for a particular zone. A lot of times we might see them drift like 5 or so amps from each other. That's fine. If you find that you have 2 legs that are pulling 30 amps and you have one that's not pulling any, that would be a problem. So we'd be looking at some type of component failure. That may be burn off wire, most likely at the transformer end. If it's a high heat zone with glow bars, we'll see the SRML wire maybe melted or burnt off where it connects to the transformer. They could also be burnt off in the control panel as well. Another quick visual check that you could do underneath the furnace is look at where the SRML wires connect to your feed throughs. If it's a high heat zone, you want to make sure that those wires are not broken, melted, etc. And before we start pulling side covers off of the furnace, we could just check fuses, things like that. Once you've checked all those and you don't find anything, it's probably time to pull a side cover off of the furnace and start checking for burnt straps, a strap touching the sidewall of the furnace, so creating a short, different things like that. And a lot of the times that's pretty visible. You should be able to see a burnt mark or a strap that's melted off and hanging. It may also be shorting against the wall of the zone. If all your current meters are pretty uniform on a zone, but if that zone is still lagging, and we're going to say a high heat zone for now, what we call a high heat zone, we typically have glow bars and a transformer in it.
if you find that zone's lagging in temperature, you could check the current draw to make sure you're getting the max current out of that zone that it's designed to handle. So what you could do is take the KW rating of your zone or the transformer. And if it's a 480 volt 3-phase zone, you can just do a simple math. A quick one for that would be to take your KW rating and multiply it by 1.2, and that will give you the max current that zone is designed to handle. If it's a 575 zone or a 575 volt 3-phase or 380, you'll have to do a little more math than that to figure out that max current draw. But if you find that that zone is not drawing the amount of current that it's rated for, at 100% output, you can probably bet that you need to tap up your transformer. Most of the time we see this first in the first and last zones of the high heat, because those glow bars are working harder than the rest of them. But as those glow bars age, they will require the transformer to be tapped up, which will give them a little more juice and bring your current draw up higher to what that zone is rated for. One of our former employees, Donnie, made a pretty nice video of troubleshooting some of this stuff, and we can give her a look here. And
So just
sounds not working.
What do I do?
off and tell them.
Oh.
Sounds off.
All right, sorry about that. Sounds like you guys may have not been able to hear that. But what Donnie's is going through in this video, and I'm sure Jess will link this to the PowerPoint here. So essentially what Donnie finds in this video, if I am remembering correctly, is he finds a bad glow bar. I believe it was broken. So again, it's been a while since I watched this video, so you guys can watch it on your own. I'm sure Jess will have it linked to the slide here.
Yeah, when I have the replay that goes out, this video will be embedded in the presentation. You'll be able to click it and be able to hear the audio of it.
Yep, so you guys take a look at that, and like I said, Donnie does a pretty nice job of troubleshooting a broken glow bar.
Okay, thank you guys very much for that. So I guess in conclusion, some of the key takeaways from today is to establish a good baseline conditions, which include atmosphere and the temperature profiles. Perform routine checks of those above profiles to help maintain furnace integrity. When a problem does occur, try to isolate that problem with some of the techniques that the guys have described and talked about today. And when all else fails, call Abbott Furnace. Or if you don't want to go through all that, just call Abbott Furnace first. On the next slide here, we do have resources on our website, abbottfurnace.com. You can see they're at the top of the navigation bar all the way over on the right. It will give you a drop down click on the troubleshooting guides. It gives you a list of the guides that we offer. You'll just have to request that information. We'll get that emailed to you. But it's also a good location or a good resource here for, we have past webinars, any information that you're looking for, you'd be able to find a lot of that, brochures and things like that in our resources section. We do have a couple upcoming webinars here to finish out the year. June 24th is our next one. Our Abbott Furnace Mexico team will be hosting that. Furnace atmosphere safety protocols. And then in September, we do have 2 of them, one for Mexico, and we also have one here for the US. September 30th, we are working on a topic, and as soon as we have that, we'll get that out to you. Next week, we will be hosting our 2025 Continuous Furnace and Brazing Symposium in Niagara Falls, New York. If it's something that you might be interested in, it isn't too late. There are still hotel rooms available to book, and we do still have some space. So if you would like to attend, again, feel free to go to that resources section of our website, go to the symposiums. It has all of the information, the flyer, and how to register for that. And I think that we'll do it. If you have any questions that you weren't able to ask during the presentation, feel free to email us at info@abbottfurnace.com. Also, go ahead and if you want, follow us on LinkedIn. That also is Abbott Furnace Company. We do share a lot of industry-specific information in there, advertise for any upcoming events, trade shows, things like that that we have coming up in the year. So go ahead and follow us on LinkedIn. So again, thank you guys for presenting, and thank you all for attending, and we will see you next time. Have a good afternoon.